Okay. So again, good afternoon, everybody. Good morning, Canada. It is my great pleasure to introduce my colleague, Masoud Khalkhali. I have known him for about a quarter of a century, which is quite a long time. I mean, they're mostly young students here, so that's about as long as we lived so far. And together with Masoud, we worked together. And in particular, we discovered coefficients in Hopf cyclic theory. This is our joint baby. Masoud is now a professor at the University of Western Ontario, or as some people call it, Western University. And he's an author of numerous papers. He's a recipient of numerous research grants. He was an organizer of uncountably many conferences.
Oh my God.
I mean, I couldn't count them, so it's uncountably many. And he's also an editor of our journal, Journal of Non-Quantum Geometry. So this is a very important job. And I might make an advertisement here, which might be illegal, but let me do it nevertheless. So he is the author of a wonderful book, Basic Non-Quantum Geometry. I really recommend it. If you want to start from scratch and learn some basic stuff about NCG, this is the way to go. And allegedly, I just found it in your CV, you are now writing a book with Alan Kohn, Quantum Geometry, right? So
yes, that's
I've seen such gossip in your CV. So. So that would be great. We are waiting this arrival of this book. And I suppose now, without any further ado, Masoud Khalkhali, Western University. Masoud, the floor is yours. Take it away.
Oh, thank you so much, Piotr, for this very kind, generous introduction. I really appreciate it. I thank organizers for giving me the opportunity to talk here as well. So yeah, so as Piotr said, I mean, I really primarily worked in non-commutative geometry, but then very recently means like last 4 or 5 years at least, through some specific questions in non-commutative geometry, and quantum gravity, non-commutative geometry applications to physics, I got into random matrix theory. I should say I didn't know anything about random matrix theory till then, but I found the subject is just amazingly fascinating. It's just a beautiful subject, and so I eagerly suggested the topic. But then I noticed that Anna also has the same topic. But when we contacted each other, it's clear that we are kind of not going to overlap that much, but there will be some basic overlap. So I hope it's okay. I mean, this is some sort of invitation to the subject. At the end, I will discuss the reason I came across random matrix theory and I started learning it. I mean, it's a huge subject, and by far I'm not an expert. So that means perhaps you will have a better chance to understand random matrix theory, because I'm struggling with it all the time as well. Anyhow, so this is random matrix theory. So one concept one should kind of grapple with first is the idea of matrix ensemble. So what is it? It's simply a set of matrices and a probability measure on that set. So a set of matrices plus a probability measure. So when you take this step, as I said in my abstract, you kind of randomize linear algebra. Then any statement in linear algebra, you can study it from some probability theory perspective, and it takes totally different dimensions. I mean, for example, if your matrix A belongs to your ensemble, I mean, then you have some random variable like trace of A. And then from here, you can study the expectation value of your random matrix. This is often a very interesting problem. Or you can look at the expectation value of determinant of A. I mean, these are just the most elementary things you can think of, but basically that's the kind of thrust of the theory at first, but we have to notice something. We have to note that the meat of the theory, the really essence of the theory is when you look at larger and larger matrices. So basically, it's like really the essence of the theory is in limit laws. And yeah, so that's what happens. So basically, limit laws and universality classes. That's the really the essence of the theory, if you want. So in this case, then it's very good to think about some basic limit laws from probability theory that you learn in undergraduate, maybe. That is things like law of large numbers. And something like central limit theorem, for example, from classical probability theory. So historically, the subject, I can say, started with Wishart. So this is Wishart matrices, 1928. Wishart was a very good, excellent statistician and mathematician who worked for Department of Agriculture in UK. And he came across the following set of matrices or matrix ensemble. So this is called Wishart ensemble if you want. So you define a map from P by N matrices, real matrices, to P by P matrices. The map basically sends matrix A to 1 over N, A transpose. So this belongs to cone of positive matrices or positive semi-definite matrices. P by P of R. So this is not a linear space, it's a cone in the space of matrices of positive semi-definite matrices. It's a surjective map, and you just need a measure, a probability measure here under this map. Well, sometimes this is called S even. It's called a scatter matrix in statistics. And so you just need a probability measure here. The way to put a probability measure over there, I just take a matrix on the left-hand side, and then you can look at columns of this matrix as random vectors, random Gaussian vectors. So these are random Gaussian vectors in RP. Random Gaussian vectors in RP, and otherwise they are independent of each other. So that fixes a probability measure here, which is essentially built out of Gaussian vectors or Gaussian measure. And then you have this matrix. And the problem that's very interesting, one of the problems that's very interesting in the statistics, and that was the concern of Wishart, is to understand the spectrum of such matrices. Now, a spectrum, of course, is going to be a random object, and you want to understand the nature of the spectrum of this matrix in this case. And that was the first problem. Some people say that actually random matrices started with Hurwitz. Maybe I just write here. Maybe that would be level 0. Not that the work of Hurwitz is level 0 work, but it's only tangentially related to random matrix theory in a way. So basically what Hurwitz did, he came from representation theory and he put a kind of invariant measure. He was the first one to think about invariant measures on or Haar measures on Lie groups like on some orthogonal groups, on some unitary groups, etc. This was related to his and Hermann Weyl's famous Unitarian trick. Using this measure, he could use this Unitarian trick and then do a lot of great results, like representation theory of finite matrices in the case of compact or maybe even semi-simple case. So this is the case, but really, I could say random matrix theory started in earnest in 1950s. So this was, can you see it here, I suppose? So yeah, let me erase this. So my third example would be the example of Wigner matrices. So this was in 1950s. So basically, Wigner wanted to have a model of Hamiltonian for heavy nuclei. There were some experiments on neutron scattering experiments from heavy nuclei, and he wanted to understand the level spacing between different energy levels that you get. So it's a very complicated quantum mechanical problem. Nobody, at least back then, had any idea of what it is. So Wigner had an ingenious idea. He said that, well, we don't know anything about it. So I'll just approximate it by finite matrix. So basically what you want to do, you want to solve the Schrodinger equation, steady state Schrodinger equation is energy. And this H is Hamiltonian. So he said, okay, I don't know anything about H, so I'm going to assume H is just a finite n by n matrices. Hermitian, because we are in quantum mechanics, right? So H belonging to m n by n C. Sorry. Yeah, Hermitian. Hermitian. Okay, so these matrices, of course, they have real eigenvalues because they are Hermitian. I mean, dimension of this H, so this is called usually Hn. This dimension of Hn is equal to n squared. It's a real vector space only, and its dimension is n squared. And another idea of Wigner was that, okay, I don't know anything about this matrix, the entries of, except that it's Hermitian. So its entries are going to be completely independent of each other. So this gave rise to the idea of Wigner matrices. So in this case, the probability measure is such that independent entries, I mean, statistically independent entries. Otherwise, each entry can have its own probability distributions. You just multiply all of them. Of course, you have to observe that there is, this symmetry. There is this Hermitian property. So you cannot take lower diagonal parts independent of upper diagonal parts. But apart from that, they are going to be independent of each other. And centered. Centered means that for normalization reasons, you assume that these guys are basically have expectation value 0. Mean is equal to 0. Okay, with this, it was idea of Wigner to understand the spectrum of this, and also the average spacing between eigenvalues. The second problem he could not completely solve, but the first problem he completely solved. He found the spectral distribution of eigenvalues in the large n limit, and he basically showed that the limiting law is independent of this choice of initial probability measures on these HNs for different n's. So if you want, this was the first limit law and the first universality class, which is the class of Wigner matrices. So there is another class, which is class of unitary invariant ensembles, which I will work with. So what you can do in this case is you put a different probability measure on Hn. Basically, you declare the probability of some matrix to be given by some function, something like 1 over z, exponential of minus trace of p of h. So this z obviously is going to be total integral. It's a normalization in this language first. But the h is the standard Lebesgue measure on Hn, because this Hn is, of course, only just a linear space, canonically isomorphic to r to the power n squared. You can use coordinates, and then you have this measure dh, which is products of all these matrix entries, real and complex separated. So this is a finite integral. You want to make sure that it's a finite integral. If you want, then v has to be a special kind of polynomial, for example, which is called potential in this case. So this is an example of unitary invariant matrix. In general, if you want to have a general unitary invariant matrix, this measure P of H should be unitary invariant. P of U, H, U star is equal to P of H. For all unitary matrices U, that unitary group acts on H, obviously, and for all H, right? So this is a special class of these things, but not the only ones. There are other types of unitary invariant measures which are not captured by this, but this is reasonably good. So the two class, the Hermitian, the Wigner and the unitary invariant ensemble intersect in one interesting class. So if you want, this is the class of unitary invariant ensembles. And this is the class of Wigner. And the intersection is a very thin set. Basically, it's the set of Gaussian unitary ensembles, which I will introduce right now. So this is GUE here. Up to some scaling, some trivial modifications. This basically, there is only one object here, and this object is going to be of this form. So this is the famous GUE, which is Gaussian unitary ensemble. So this is like the probability measure is given by the following things done over Z GUE and e to the minus n trace of 1/2 h squared. You see, notice Gaussianity is in the fact that it just shows this quadratic polynomial, in this case, just h squared or x squared polynomial. And this n is a very important factor. I cannot explain why it's a good idea to put it here, but it has to do with the scaling issues. If you don't do that, you have to do rescaling later on, but it's a very good idea to put it there. This 1/2 is also very important, but this is a normalization constant as well. So this is the famous Gaussian unitary ensembles. So Wigner or maybe Dyson, so this is sort of threefold way, so to speak. Each of these three skew fields of mathematics, R, C, and quaternions, have their own unitary invariant ensemble. So we have so we have this symmetric. So we have this Gaussian unitary ensemble GUE. We have this GSE, which is Gaussian symplectic ensemble. This has to do with quaternions H. This has to do with C. and there's a class that has to do with all. We can call it Gaussian symmetric ensemble or something. Oh, it's called GOE, by the way, Gaussian orthogonal ensemble, GOE. Same type of definition, you work over R. Same type of definition, you work over quaternions. Same type of definitions, you work. So these are the three famous classes that are relevant for things. But notice that this is really the simplest type, because it's like when you study quantum mechanics, you look at the case of some Hamiltonians where the potential is just the kinetic term. There is no really potential in a way. So this is kind of interaction-free version. This is the simplest, most primordial example of an invariant ensemble. And here there is a lot of other things which are far more complicated to study. And here there's far more complicated. And the whole thing, the union of the two is not even the whole thing, because the whole thing is much bigger than the union of the two, of ensembles of Hermitian matrices. Anyhow, so maybe at this stage I ask if there's a question.
Go ahead, Adam, but you should grab your mic. Yeah, there is a question, just a second.
Okay, good, yeah.
Okay, so could you hear me?
Yes, yes, I can hear you, Adam.
Okay, so my question is related to this approximation of this Hamiltonian, since
yes.
Usually in quantum mechanics, almost always, this Hamiltonian is some sort of infinite dimensional unbounded operator. So in what sense do we approximate it by random matrices?
Well, I mean, yeah, so I think his idea, Wigner's idea, was to cut down the space, the Hilbert space. You just, it's like an idea of cutoff in also quantum field theory. You cut off, you know, your space size, Hilbert space size, from certain up to certain modes, and then you work within that Hilbert space. I mean, this can be useful, can be just leads to not interesting results. I don't know really more than that one could say. So it's just maybe we can discuss this during the discussion session later on. But that's a very good question.
Okay, thank you. I will be happy to discuss it.
Yeah, sure. Okay, so so now let me give you a so sort of do a problem or example of this thing. Actually, the example that Wigner did first. So this is called Wigner's surmise. Okay, so to give an example, let's look at a matrix A, which is 2 by 2 symmetric matrix A, B, B, C. Okay, so real symmetric. So you have two real eigenvalues. Let's put them like λ1 less than equal to λ2. Then this quantity S, the spacing of the between the eigenvalues, λ2 minus λ1, is obviously a random variable. Of course, λ1, λ2 are also random variables, but the difference is a random variable. So this is a spacing between eigenvalues. And what you want to know the probability distribution of this. So in other words, you want to know how eigenvalues of such matrices are distributed in a way. I mean, the distance between eigenvalue, according to what law it is distributed. I have to tell you what is the probability measure here. The probability measure here is GOE. So as we studied, so basically probability of some matrix A is 1 over Z GOE or GOE. This is exponential of minus something like 1/2 trace of A squared, right? Okay, so now this space is 3-dimensional. So you have this probability measure on R3 and you want to find the expectation value of this. So for expectation values, I always write this, lambda2 minus lambda1. No, I don't want to know the expectation values in this case. As I said, I want to know the probability distribution of this.
Sorry, Masoud, can you remind me what the Z stands for?
Say it again, please.
Z, the denominator, what does it stand for?
Oh, the Z here?
Yes, Z, yes. Yes.
Oh, yeah, this is the normalization or partition function. So Z is the total integral. To make sure that this is normalized. dA, dB, dC.
So are you then talking about a density function? P of A is the density.
Yeah, this is a density function. Yeah,
Okay.
I'm rather informal. Yeah.
Thank you.
Yeah, sure. This is a density function. And this is the normalization, which in statistical mechanics, this is called partition function. It's a very important object in physics. But for us now, it's just a normalization. Is that clear, Piotr?
That's clear. Thank you.
Okay. So now we can just look at the probability distribution of this. So let rho of S be probability distribution of S equal to lambda 2 minus lambda 1. It's a probability measure that exists only on the right-hand side of the real line, of course. So by general things in probability theory, you know that this rho of S is obtained by some integral, again 1 over Z. So Z, QE, integral e to the minus 1/2 raised of A2, delta function S minus lambda 2 minus lambda 1. This is dA, dB, dC. You see?
May I have a question?
Yes.
In this physics application, those lambdas usually corresponds to some energy levels, yes? But the
That's
difference is exactly what we observe in atomic spectra, yes?
Absolutely.
Like a light absorption spectrum and emission spectrum, yes?
Exactly. It's the energies that you measure. Yeah, that's why you're much more interested in this object. Yeah, exactly.
Okay, thank you.
Okay, yeah. So this is a recipe from probability theory, which this is delta function. But the thing is, this is an elementary integral. By some change of variables or other means, you can compute it. And rho of S turns out to be given by actually equal to S over 2 exponential of minus S squared over 4. This is for S bigger than or equal to 0, and 0 for S less than 0, which is not surprising because it's a positive quantity only. So if you draw this, this is looks like this curve and then rapidly dies. This is S as a rho of S. So this result was obtained by Wigner. Most probably this is the first result that was obtained by him. And this kind of, this is called, you know, such probability distribution, this is called Wigner's surmise. The reason it's called Wigner's surmise is that, of course, one is interested in general case. What is this similar integral over 3-dimensional, 4-dimensional, 5x5, 6x, n by n matrices? And it turns out that this is an actually extremely complicated problem. So most of random matrix theory is about computing these strange integrals, but there is something there that it takes a lot of time to discover, if you ever discover them. And this could not be done by Wigner, only by 2 case. And he surmised that the general case is going to be similar to this. So, okay, it turns out that he was right. The general curve is rather similar to this, but its expression is much more complicated expression. It has to do with infinite dimensional determinants and Pfaffians, infinite dimensional ones, and some very exotic mathematical objects. So this is the case that it's kind of very good to kind of grasp at first. Now, what is the task? So, so this question is very difficult, but Wigner, as I said, was very successful in finding the case of the spectral distribution of n by n Hermitian matrices in the limit. So there is an object I want to introduce. It's called the spectral density function. So this spectral density function is, so if you want, there is a map from n by n Hermitian matrices going to P of R. So this is the set of all probability distributions on the line. All probability distribution is an interesting set, is an interesting space. So this map is mu n. So what is it? I mean, basically mu n of some Hermitian matrix. Totally deterministic map is given by 1 over n, some delta functions of x minus lambda I of h, I from 1 to n, right? So basically, you look at eigenvalues lambda 1, lambda 2, up to lambda n of these n by n Hermitian matrices, and this is it's a discrete probability measure that you obtain for each individual h, right? So basically, what you get, you're going to get some spikes of some delta function here and 0 delta function, and adding them up. All right, so for now, this is very difficult object to work with in general. So you want to average this. So what is the, first of all, what is the interest of this? You see, if you 1 over n number of lambda in the spectrum of H, such that lambda is between B and A. So number of lambda that is in the spectrum of H that is located between B and A is exact, I mean, the average number of the spectrum. This is exactly equal to integral from A to B by definition, mu n H dx, as you can see, right? So this is one, so this basically, this measure tells you for each A and B, how many eigenvalues are located between A and B with multiplicity. We are counting with multiplicity here, right? Now, there is something very, very nice here, which you have to notice. And the question is the nth moment. Let us note that the nth moment of this mu n h, this is by definition nothing but integral over r x n mu n h, after all, is a function of x dx. This one. Now, this object, if you are integrating xn against this measure, obviously this is going to be equal to 1 over n sum of lambda I to the power n of h, I from 1 to n, which is 1 over n trace of just h to the power n. This is something we have to observe. And it's very elementary computation. The nth moment of a spectral density function is 1 over n trace of hn. Okay, but now this object, as I said, is complicated. So you want to average this. So what you can do, you can just go by this process of averaging. You average over all h. So this is called mean density function, maybe. So this mean density function, let's call it rho n. Still there is this level n, we are at level n, capital N. Rho n of x is equal to the average of mu n. I mean, this average is not a problem. This is a rather complicated object because it's a probability valued random variable. Okay, so yeah, it's a bit, but making sense of this averaging, it's not a problem. And once you do that, you notice that already this discontinuity disappears, and this turns out to be a smooth function. I mean, at least for these unitary invariant ensembles that we are going to work with. So from this thing, which is basically histogram in a statistics, that basically produces the histograms.
Masoud, excuse me, could you hear me, Masoud?
Yes, yes.
I don't see the second blackboard. I don't know if other people see. I just
sorry. Yeah, I'm sorry. I'm off here. So yeah.
Generally it's great, but you know, it's just stay at one blackboard, you know.
Yeah, that's a good idea. So let me then maybe I will change it to this, and then I will start from here, huh?
Oh yes, now in the left there are more space. Yes.
Is this better? Yeah, I think I can start from here somewhere, right?
Oh yes. Okay.
I can start. Thank you. Yeah. All right. So I just stop there. That's a good boundary, and the left boundary is here. All right. So this object then is basically this rho nx, the mean. With respect, of course, to this measure, that probability measure you're working with, it typically looks like this. Still a very complicated smooth function, but it's a smooth as opposed to this sort of things. And now the problem is the following. The problem of larger limit distribution or spectral distribution, whatever, is the following. So we just say that this rho nx converges to some probability measure rho of x on the line as n goes to infinity. Now this convergence is in some sense, okay, because it's a function, and we want to say it converges to some function which in some sense. For example, you can think of it as in a very weak sense. You can say, for example, moments of this guy converges to moments of this guy. So, for example, the nth moment of here converges to nth moment here on the right-hand side. I dropped the x. Maybe I should put it. As n goes to infinity. Now, this is a very well-defined object because this is a number, and this is a sequence of numbers converges to this number for all n. Moment to moment, all moments converge, and this law of x, then we can say that, okay, it captures the large and limit distribution of eigenvalues in some sense. At what Wigner showed, so let me write this result, then I will sketch a proof in some cases, because that's a proof that kind of interesting. So this is the famous Wigner's semicircle law. So this was done by Wigner's mid-50s. So basically, he showed that for Wigner random matrices, basically for any initial choice of probability distributions, the corresponding rho n of x converges in moment. I believe Wigner only did the moments case, not more delicate cases, moments to rho x. But this rho x is a semicircle. Is 1 over 2 pi integral, square root of 4 minus x squared for absolute value of x less than or equal to 2, obviously, and 0 for absolute value of x bigger than. So this semicircle, it's really just a semi-ellipse, not a circle. That's okay. Minus 2, 2, and this is the thing. So what does this say? It says that if you are given a large random matrix whose entries are distributed according to Wigner's distributions, which is very general, but they have to be independent of each other, then the probability of finding eigenvalues between some numbers a and b is going to be the area under this semicircle curve. So this is the famous semicircle law, and that's the case where we are going to actually look at. So what my plan is, I'm going to focus on a proof of this, quick proof of this. In the case of not Wigner matrices, but in the case of a special class of Wigner matrices, namely for Gaussian unitary ensembles, because that opens up some other very interesting issues that will appear in many other places. So, any questions so far?
Any questions? Masoud, can you hear me?
Yeah, I can hear you.
Perfect.
Yeah.
Okay, so no questions in the room.
Okay, cool. Great. So let me now sketch a proof in the case of UE. Sketch for UE. One of the most interesting things about this is we want to know the expectation values of traces of Hn. Right? So if you notice, this is really just 1 over Zn GUE integral trace of Hn into the minus n trace of H2 over 2 dH. So the question is, I mean, why we are looking at this? This is, of course, the nth moment of these random matrices that a spectral distribution of H, mean spectral distribution, as I showed over there, right? So, and we want to compute this, and we want to show that this actually converges to the nth moment of the semicircle law, rho semicircle x dx over r. Of course, this is 0 for n odd, right? Independently, we know that this is equal to 0 for n odd because of symmetry reasons. And then, I mean, the integral is elementary, right? So, so let me write it basically. It is root 4 minus x squared dx. I mean, indeed, it's just between minus 2 and 2. And it is just 1 over 2 pi normalization factor. And you can compute this integral for n equal to 2k even. And this comes out to be ck. This is the kth Catalan number. very famous combinatorial object, CK.
Masoud, whatever you write on this right blackboard is invisible.
Oh, yeah, I'm sorry. Yeah, I'm sorry. I forgot. Yeah, yeah. So this is for n equal to odd. I hope this is okay now. And this is
Yeah, it's perfect now.
for n equal to even, equal to 2k. Now, CK is the kth Catalan number. So this kth Catalan number is, you can compute it, if you open up this book of Combinatorics 1 by Stanley, there are, I don't know, maybe 100 at least different definitions of Catalan numbers. And there's an exercise to show that all of them are the same. So it's an amazingly rich combinatorial quantity. It's 1 over k plus 1, 2k, choose k. All right, so we want to show that this left-hand side, this Gaussian integral essentially converges to this number. That's what entails proving semicircular law. Okay. Now, Gaussian integrals, there is a magic kind of idea in computing Gaussian integrals, which has to do with Wick's theorem. So using Wick's theorem, for Gaussian integrals. So imagine you want to compute the expectation value of products of two random variables or two variables xi, xj. So this would be xi, xj, e to the minus 1/2 the following integral x transpose a x dnx. So this is a very general result. A has to be positive definite. This is a Gaussian integral in the n-dimensional space for any, I mean, maybe I'll just put n, it doesn't matter. Yeah. For any n-dimensional space, this integral, it's actually equal to a inverse ij. So this is what in quantum field theory it's called propagator. I mean, this is a toy model, of course, zero-dimensional space, but the same idea. The matrix entries of the inverse of this operator in quantum field theory, this A, which is a positive semi-definite or whatever, it's replaced by Laplacian and things like that. So this is the inverse or basically the green function at component ij. That's the matrix entries of the inverse of the operator. So this can be interpreted by saying that you can compute the inverse of matrix using probability theorem, if you think about it. But this is not the Wigner's law. So Wigner generalizes this. So that's what we need. So let me just write it down. So then basically xi1, xi2, xi maybe 2k. So this is this is Wick's theorem. Sorry, I said Wigner. Maybe this is Wick's theorem. So this is equal to sum of product of xi, xj. So let me write it like this. Over sigma, a pairing of the set I1, I2, I2k. So this is a combinatorial device now. You see what you do, you're supposed to put these things on a sort of graph, simple graph. And then the pairing of such a thing is, so let me give you an example. What are the pairings in this case? So for example, imagine you have 4 of those. So this is one pairing. You can compute, you can define another pairing, which would be these two. And there is another pairing. Okay. So this means that in order to compute, for example, xi, xj, xk, xl, the next case after this, you have to sum. You have a sum which is over 4 elements, pairings here. Okay. So and then basically this by that elementary result is going to be A inverse ij. So it's basically products of matrix entries of the inverse matrix taken 2 by 2 by pairing like that. So this is a primary device in quantum field theory and also in probability theory in order to compute such things. And using this now, there is a kind of interesting nuance appears in this case, because the nuance is that we are not, you see, this is a general n by n, I mean, this is general matrix. This is, I mean, this is general integral, Gaussian integral, but this is really, we are summing over matrices. So there is an extra structure embedded in this Gaussian, which is not visible in this case. So this was used by physicists first and then mathematicians in order to compute these things. So let us write it. Of course, this is just nothing but, you know, sum hi1, i2, hi2, i3, hi3, i4, and then sum hin, i1. You come back, right? Yes. Overall, I1, I2, In, right? It's a summation. We are going the way that matrix works, matrix power trace works is of course like this. And so you are in a setting to use this Wick's theorem in this case. But if you are not careful of the structure of matrices, you may get into some trouble. But what people notice, in fact, starting with Hooft, you notice that the summation, instead of summing over such graphs, can be summed over polygons. So let me now write it like this. So we want to compute such things in this case. So the idea now was, so let me give you an example. For example, what is, you know, this Hij, Hij, HJL, IJ, JL, HLK, H, well, I'm using some HLM, MI. The next case, so this would be trace of H2. Expectation value of trace of H2. H4, sorry, trace of H2. So there is a result that you say, so I mean, so you have to know this, Hij, HKL is equal to 1 over n delta IL delta JK. So in other words, this expectation value vanishes unless J is equal to K and I is equal to L. Otherwise, it's 0. And when it is non-zero, it's 1 over n. Because of the scaling that we did after. So this is like the analog of this result that we had. Remember? Xi, Xj, using that result, but each X has a double index, right? So that was like A inverse Ij. This directly leads you to this result with a little bit of K. All right, so now we can, so this is a general thing. Now we can use Wick's theorem. And you can do the following thing. The trick is you put everything on in this case, H4, you put it on a foregone, I mean, regular or whatever, foregone. So I, J, K, L. And you notice what you have to do. You have to do gluings of such things. So is one gluing. Okay. So K links corresponds to gluings of these things across these edges that's singled out, right? These two. And then there is another one, which is quite similar to that one. So basically, you're decorating these polygons by these values, Hij, and when you pair, it means that you're multiplying this Hij with Hil, and then Hjk with this one and so on, in this sort of big expansion. Okay. Now, something happened, very interesting happens in this case. You get a surface when you glue these things. So you get a closed surface. So basically, sorry, in general, if you have a 2n gun, for example, one of these even or more, this any sort of gluing, etc., gives you a surface. So it actually, I mean, gives you a closed surface. It actually gives you more than a surface. It gives you a surface plus a graph embedded on this. In such a way that the complement of the graph is contractible. It's just a two cell. So such that its complement is a two cell. So it's contractible. So let's look at this case, for example. What do we get in this case? So if we do this, we're going to get a torus in this case. And the graph that you get is this graph, embedded graph. This one. The complement is just some two cell here. If you do this, you get a sphere. And the thing that you are identifying, so basically in this case, all four, these are, that's what you get. Now, this, so you notice that then the summation, this trace can be understood as summing over surfaces. So let me now write down a little bit of sort of Euler characteristic of such surface for you, and then I will compute in terms of Euler characteristic. So, so now let f equal to 1. So this is number of faces. And then E to K, this is number of edges. The reason is that we have 2 K edges and you identify them 2 by 2, so you just end up with K edges on the surface. And V is equal to some number, which is again, 1 is a number of vertices. So Euler's a great formula is that the Euler characteristic of this surface sigma of course, is going to be given by number of vertices minus edges plus faces. That you using this data that you start from the graph, you get b minus k plus 1. This is 2 minus 2g, where g is the Euler is the genus of the surface. Okay, so this is what we know from topology, that genus enters into this Euler characteristic formula this way, 2 minus 2g, right? So then the expansion that we are interested in can be understood like this, then 1 over n, expectation value of trace of, let me write it as h2k, for example, yeah, is sum over sigma n to the power, sigma is the gluing that you're using. I mean, certain identification of edges of your 2k polygon, right? So n to the power vertices of sigma minus k minus 1, and using this Euler characteristic in terms of genus, you obtain something called genus expansion or topological expansion. In this case, get genus expansion, also called topological expansion. It's a very simple case of the general fact. So this is basically equal to, I write it as sum g from 0 to infinity, epsilon j k n to the power minus 2t. So these epsilon j k's are very important combinatorial numbers. They are extremely difficult to compute. There's no general formula known for them, but this was first derived essentially by Harrer and Zagier in 1980s. They were interested in computing Euler characteristic of orbifold Euler characteristic of modular space of Kerr. So their concern was totally out of random matrix theory, but they found random matrix theory language extremely useful to express this. So they have a recursion formula for epsilon jk's, but there's no general formula except one case which we are very interested in. So case we are interested in is the case where you get when g is equal to 0, the leading case, because that's the case that controls the limit as n goes to infinity, right? So limit of course, that's obvious from the definition that we have. This moment is exactly epsilon 0k. Huh?
Masoud?
Yes.
Talking about limits, do you think about converging towards the end of your lecture in some reasonable topology?
Yeah. If you give me, is it okay if I have 5 minutes?
Yes.
Yeah, 5 minutes. I'm done. I promise. Yeah. My apologies. I'm sorry.
No worries. No worries.
Yeah, okay, very good. So we have this. So this is epsilon. So these epsilon 0k's are called planar. Well, this is called planar limit. And these are planar diagrams. So this is exactly the cases where your Riemann surface is a sphere. Sphere. That's why it's called planar, because if you puncture a sphere, it's isomorphic, homeomorphic to the plane. These are called, physicists call them planar. So this is what we want to know. And then you have to notice one fact, which is easy to prove actually. It's not too difficult, I mean. The fact is that actually you get a sphere if and only if your original gluings are non-crossing. So sigma of is a sphere if and only if little sigma, which is the gluing, is a non-crossing diagon. Is a non-crossing gluing. So what does non-crossing mean? Well, non-crossing is intuitively clear. So let's look at the case of maybe 4x4, the non-crossings. So you see, this is the crossing case, right? Because they just cross each other. The gluings cross each other. So this leads to torus, as we can see. So this is not good because it's the next term in the expansion, which we don't want. But there are two cases where you do get, you get the sphere in this case, and for this one also, sorry, you get the sphere again. So in two cases, you get a sphere. So this contributes the term of 2 for H2. And so now the question boils down to counting number of non-crossing gluings of a 2K gon, right? So the limit then is equal to, according to what I said, is equal to number of non-crossing gluings of, or pairings of a 2K gon. So this is now purely combinatorial problem, and you can write recursive relations for these things. That's very easy. So the recursion you get, if you call this CK, you get CK is equal to some, I believe, CK minus I, CI, I from 1 up to K or something. I from 0 up to K. Yeah, so this is CK plus 1, I from 0 up to K. This you can, I insist, this you can absolutely prove by totally elementary means. I mean, this is just, you can write, you can count K plus 1 crossings, non-crossing gluings in terms of the lower order non-crossing gluings by dividing, by chopping, for example, in this case, this and chopping that. It's completely, and this is exactly one of the recursion relations for Catalan number. Okay, so this is one of the famous of recursion for Catalan.
So it's one of these 100 equivalent definitions.
At least 100, yes, exactly. But this is sort of very important, one of the most important ones, because this recursion is a kind of beginning now of a very beautiful story. So this is the beginning of a beautiful story. The story is that this recursion for more general random matrix models where you have more complicated potentials, actually people showed later on that there is a corresponding recursion with some added terms, much more complicated. It's called topological recursion. And so that's what's going on right now, or in the last 10 years, 15 years, at least, something like that. Even for more general quantities than just simple moments. But using this, you can prove, using a generating function technology, that this is exactly the Catalan number. And so this proves the Wigner's semicircle law for you. This is the topological expansion or genus expansion proof of Wigner's semicircle law. I chose it because it's kind of relates to a lot of other issues. It relates to quantum field theory, Wick's theorem, this sort of, Riemann surface theory. Actually, this is completely topological, but once you do topological recursion, actually you land in some very exotic aspects of even complex Riemann surface theory. So that's a very interesting thing. So I'm sorry I went over time. So thank you very much. I'm done.
Thank you so much, Masoud. Let's thank Masoud.
I meant to discuss, maybe that was overambitious, to discuss the reason I came across this, but well, we can just discuss.
Yeah, don't worry, we'll drag it out from you in questions. So any questions from the room before we go to Zoom? No room questions. Okay, so Zoom questions.
Okay, so if I may come back to
yes,
this
please
question regarding this Hamiltonian. So my concern is that after all, what you are getting in this random matrix theory is something which is bounded. You get a semicircle, but if you take unbounded operator, the spectrum is in particular unbounded. So in which sense do we approximate it?
Yes. Okay. So yeah, that's a good question. The reason we are getting this semicircle is because of rescaling. You see, this thing that I showed, in fact, you're quite right. A Hermitian matrix, the spectrum could be quite scattered, and for larger and larger matrices could be quite all over the place. But you know, we basically used two things: 1 over n, like trace of H2K, right? We wanted to compute this. But remember, the measure we used, that's scaling we used, was the following. We used 1 over z integral the minus n trace of H2 over 2 dH. So as n grows, this actually decreases the effect of larger and larger eigenvalues. It basically compresses the thing. So let me put it this way. If you don't put n here, you get infinite. So it's like a central limit theorem. If you don't divide by 1 over root n, exactly 1 over root n, I mean, divide by, sorry, by root n, not divide by 1 over. If you have to exactly divide by root n in order to get a sensible object. If you divide by anything else, you don't get central limit theorem. And that's exactly the point. Scaling is very, very important in probability theory. So if you don't have that, then we have to put 1 over n. And we do that. You have to do that. So this would be like 1 over n to the k, trace of H2k with respect to this quality measure. So maybe that will give you a little bit of comfort, Alex, if to know this, that scaling is very much involved in this. And the second thing is, yeah, I mean, of course, at the end of the day, as Freeman Dyson said, the dream of Wigner was basically completely demolished eventually. They found that this distribution is not useful for the problem that they wanted to know. And then quantum field theory spectrum, I mean, the Hamiltonian of heavy nuclei, I don't know, I'm not an expert, but this, I guess, is captured by maybe standard model or maybe not. I really don't know. I mean, so they were, I mean, in 1950s, it's, I don't know, from one point of view looks quite old, but from another point of view looks young, because the standard model was developed starting from 60s, basically. So then as far as physics goes, a lot of more insights came into this. But amazingly, the problem that started from physics like this, it became extremely useful in other areas, including mathematics. For example, the connection between distribution, exactly this sort of spacings of zeros of Riemann zeta function on the critical line, and or maybe critical spectrum, and the distribution of eigenvalues of random matrices, Hermitian or unitary, doesn't matter. It's there's some hope for people to approach the Riemann hypothesis, but even that's a big word. I mean, like throwing big word. I'm sorry. There are a lot of beautiful applications of random matrix theory in everywhere, in machine learning, artificial intelligence, in biology. in everywhere you can imagine, in combinatorics. I mean, like in the case of Harrer-Zagier, in case of like topology of moduli spaces, and there are all kinds of things. So I think the subject is really justified by its eventual applications to different fields. So.
Yes, for the overall picture, I don't have any doubts, but I was only focused on this example. So as I understood you correctly, the situation is that this was an attempt to solve a particular problem in heavy nucleus quantum physics. Yeah. But then it turned out that for this specific problem, these attempts turned out to be not satisfactory, yes?
Absolutely, yeah.
I see.
Yeah,
okay, and maybe just one more small question related to that. Do you know what physicists consider as heavy nuclei, starting from which atomic number?
Oh,
helium is already heavy, or everything
no.
Hydrogen is heavy, or
No. I think you have to go really way in the Mendeleev table, high up atomic numbers, really high. I don't know. I really don't know. That's one of those catchwords again. That okay. So the thing that they did was it with radioactive material they were doing neutron scattering, or I don't know. But this you can find reading some basic papers, original papers, like maybe even in original Wigner papers, which is all published, of course, again in volumes, collected works and other places. You can even see graphs of things that they came out labs. You can see that's kind of nice to look at those graphs. Yeah.
Okay,
I really don't know. Very good question.
Yes, but since it came from something which is radioactive, so this is already something which is heavy. Yes, it's not like like a carbon or something. Yes.
No.
I think greater than iron. It's that's considered heavier.
Which one?
Greater than iron, ferrous.
Sorry, I don't. I missed this.
No, the elements that are atomic number are greater than iron.
Iron, okay, iron.
Oh, greater than iron. I see. Oh, okay. Well, okay, very nice. Okay, what is the atomic weight of iron?
I think 56.
56. Oh, okay. Well,
that's why it's so heavy to carry. Yes.
Because after that you have this neutron versus proton ratio gets greater than 1.
What is greater than 1?
Neutron versus proton ratio. Number of neutrons versus proton.
I see.
Okay.
I see. Okay. Yeah. These are things.
Yes, after all these questions are just ordinary quantum mechanics. Yes, but okay, very difficult. But quantum field theory is not entering.
No.
Yes. This is just ordinary quantum mechanics.
Yeah. Exactly. Yeah, I should say Wigner got inspiration. He got his inspiration. Of course, he had a very nice problem to tackle with, but he got his inspiration by looking at Wichard's paper. So not Wichard's paper. Wichard's actually ensemble appeared in a text on multivariate statistics. He said, I went to my office one day. This page of the book was open by chance. I looked at it and said, oh, this is exactly what I need. So this is quite serendipitous.
That's random page theory.
Yeah, random page theory, something. So yeah, I mean, Wichard, by the way, didn't do more than computing that density function. The spectral density, I mean, computing the probability distribution. But by the way, that probability distribution is a vast generalization of like chi-squared, this sort of things, squaring things, distribution. But the actual spectral distribution was considered by Marchenko and Pastub. I believe Anna talked about it this morning. Yeah.
Anybody else? Any other questions? Adam, I understand you are unsatisfied, right?
Yes, I'm happy. I'm very happy with the answer. Thank you.
Okay. Adam is happy means that maybe.
Okay, I have a comment. I mean, baby steps disappeared, but I have a comment.
Yes, please.
I think I want to thank you very much for the great lecture. It was a great lecture, and I will explain you why. When we organize such schools, you know, then it's very difficult to explain to the speakers how to talk to undergraduate students.
Yes.
And I think you have chosen a perfect method. It was an ideal lecture for undergraduate students. Thank you very much. I mean, it's a model lecture. I'm really very happy.
Thank you so much. I really appreciate your comment. Thank you. Thank you very much. Yeah. Thanks a lot.
I fully concur with Eva, of course. And let me end your lecture with a question which you suggested yourself. So how
Yes.
come an uncommuted geometer, how yourself fell into the arms of random matrices? And is it in any way related to these wonderful and impressive symbolic calculations that you were doing when computing these terms of curvature and so on, you know?
Yeah, right. No. I mean, so that's totally different.
Uh-huh.
It's not that at all. I mean, but computer calculations here are also used very much. So if you look at my last 5-6 papers, not the one that we posted today, by the way, which is about Hopf cyclic cohomology. I don't know if you noticed or not, but anyhow. So what is so this is called quantum gravity, the toy model. This is toy quantum gravity. So you just start with the finite spectral triple. So as you know, it's a triple A H D, and if you want, A is a finite dimensional C-star algebra. Even you can take it simple. You can take just A to be Mn of C, really. And there are ways to classify this according to some schemes. There are different classifications, but basically D is a matrix and H is a finite dimensional Hilbert space. You can even take H to be the same. And this is acting by left regular and right regular action, things like that, right? So I'm just, then there is a model which is integration over all Dirac operators. Exponential of minus something like G trace of P2 plus trace of P4. Now, notice that this D is a Dirac operator, but it's a matrix. It's acting on some finite dimensional vector space, so it's an operator again. And so this is some sort of partition function for toy quantum gravity. Why is it toy quantum gravity? Because I mean, what is the goal of quantum gravity is to integrate Einstein-Hilbert action of metric G, this quantity, and over a space of all metrics. Because the Euler-Lagrange equations for Einstein-Hilbert action, of course, is Einstein's field equations. So this is the classical limit. And in general, by Feynman's recipe, we have to compute over all metrics, basically. I mean, let's be very, very naive and just, so this is kind of idea you want to do. So now, Dirac operators, we know that these are metrics in non-commuted geometry, according to Alan Kahn's, philosophy and ideas of non-commuted geometry. This is really a space of metrics. And here I have to put some measure here. So there are some natural measures on the space of metrics, because this is a space of, essentially turns out to be space of Hermitian or anti-Hermitian matrices, things like that. So there is a natural measure over there. And so this G is not this one, I'm sorry. This G is a totally different one. It's a coupling constant. So this model, I was kind of lucky. I was in a talk by John Barrett when he talked about it. I can write it correctly, maybe double R and double T, I'm not sure, maybe one R, double T, I'm not sure. So John Barrett was in Perimeter Institute, he was talking about these things and he was explaining his work with L. Glaser. What they did, they replaced this model by this toy model and they wanted to study, for example, phase transitions in these things. So they did a lot of computer simulations, a lot of computer simulations. And they noticed that for some values of the parameter, there is phase transition. They found spectral distributions of these things and also a spectral distribution of, I believe they only work with the spectral distribution of P. So when I saw that, I just knew a little bit of random matrix theory, very basic, very little, really nothing. But I thought that instead of simulations, we should be able to use random matrix theory techniques. I mean, so because this, you can write it in terms of this age. So for example, this D of A, the Dirac operator, can be in some cases written as commutator of A with some Hermitian matrix or anti-commutator with some anti-Hermitian matrix. This can happen. So basically this integral, then we can write it over maybe some, in the simplest case, simplest case, as some minus trace of V of H. But this V is nothing like this. It's a very complicated potential. If you write everything in terms of D, I mean, this trace of Dirac, if you write it in terms of trace of Hermitian, then you get into something much more complicated. So we started analyzing this. So that was the beginning of things. So one of the things we proved was actually rigorously we proved phase transition in that case. We also found the spectral distribution, and then there is some series of papers. I think we have so far 5 papers, but I mean there is some more work we are doing. So that was my entry into random matrix. But it's really a huge subject. It's an amazing subject. It's a huge subject. It's there's a lot of beautiful stuff going on there. So. And it's very well connected to NCG. Very well connected to NCG.
Yeah, I see it now. Yeah, this is a very good answer. Thank you so much. Thank you again. And it's been a long day. It's been a very sad day for humanity because not only we had to call off our moon mission, but also the internet in the Banach Center collapsed like infinitely many times. So today has proved to us that human technology is still very unreliable. But we will push on and we shall overcome, I hope. But today we call it a day, and on the positive note, I'm happy to announce that the morning lectures are on our YouTube channel, so you can watch them. And the recordings are much better than what we experience here in the lecture room. I mean, somehow Zoom is smart that when X collapses, it goes to X2 and so on and so forth. So it's actually quite impressive how Zoom manages recording by the host or the other host collapsing all the time. So I encourage you to subscribe to the Banach Center YouTube channel and a playlist and look at the lectures. And it's a much smoother experience that we have.
Thank you very much.
Already, you deserve lunch for sure. So thank you again for a wonderful lecture. And that's it for today. Thanks again, Masoud.
Thank you. Yeah, wonderful. Yeah, have a great day. Yeah.
All the best. Thanks.
Thank you. Okay.
Thank you.
Okay. Okay, so I just say goodbye then. Yeah.
Thank you. Goodbye.
Goodbye, Adam. Thanks for interesting questions as always.
Thank you. Thank you. Finally, somebody clarified for me this topic.
Masoud, you are again host. Could you please stop the recording?
Oh, so end meeting for all?
Yes. No, stop recording.
Oh, yeah. So how do I do that? So let me just, okay, so exit full screen and stop recording. Okay, so, oh, where is, stop. No, no. Where do I get stop recording?
Three dots, as usual.
Oh, on the top. Oh, yeah. Okay, yes. Stop recording. Yeah, sorry. Yeah. Stop recording.